As we look forward today, this event, this is the second in a series. And the idea behind this series was to get us all together as a community and to have a series of discussions with those that impact our times, with those that can help us think through, but to add one additional element to that. The idea was to talk about at these events, to have those topics of strategic importance to the university, with the goal of not just being together and working for our collective intellectual selves, which in and of itself is important, but also to help all of us understand better those areas of excellence for the university and those areas where we plan to expand and increase our investment to advance not just this institution, but society as a whole. And that brings us to the topic we have today. And this will end at some point in time. We will eat dinner and then we'll actually have our speaker, but I'm having a ball. So I get it. Some of you are looking tired. I'm not. I will wrap this up soon. All of us that are Oklahomans understand the importance of impact of weather, and all of us that are part of this university community understand how important it is to us in terms of our strategy, about who we are as an institution. Right? We all know NOAA, which probably isn't known around most institutions, but it's a National Oceanic and Atmospheric Agency Storm Prediction Center, housed here at the National Weather Center at the University of Oklahoma. And our atmospheric researchers are at the absolute forefront of this. And objectively, by these measures, OU School of Meteorology is the largest and most respected program in the country in the space of atmospheric science and meteorology. We're in the top 5 in National Science Foundation NSF grants. I see John Snow here as well. And the potential and the reality of becoming number 1 in the very near future is definitely on the horizon. The infrastructure is stunning. We've all driven past it. We know what the importance is. But back in 2006, we made the investment. And this is how you advance great institutions and great enterprise that impact us all. The state and federal government and the university all came together and built out the National Weather Center, a stunning facility of almost 250,000 square feet of research space, now populated by 800 scientists. World-leading scientists that is a partnership between NOAA, the best and the brightest in the space from NOAA, and OU PhDs and researchers across the space. In every aspect, this group transforms society. Right? And we want to talk about the commercial aspects. But at the end of the day, institutions, we do spin off commercial enterprises, and that's important. And we certainly have those that are here, right? The North American headquarters here of Weather News, a major and growing office with DTN and other enterprises. When you think about what the forecasting capabilities and the storm prediction efforts are that are taking place and the advances that are occurring, it is stunning. And we are not just increasing our investment, we're aggressively increasing our efforts in these areas. And good examples of what we're doing in this area. We're expanding beyond the short-term forecasting, looking at sub-seasonal forecasting and seasonal forecasting. A dear friend of mine who's right here said, "You mean like the Farmer's Almanac?" I found that sad too. I'm going to give him a special course in this. The rest of us know how this works. When you look at the impact, right, every industry in our country, in our world is impacted by weather. And speaking of global impact, the $161 million in funding that we received through NASA's Earth Science mission to build the GeoCarb, the Geostationary Carbon Observatory, is something that is exciting. It's going to launch into space in the early 2020s. And it has the ability to look down and monitor from space the globe and carbon cycle and how it's changing and monitoring the changes in plant health and vegetation stress throughout the Americas. This is the sort of work that is going on here. If you don't know about it, it's worth knowing about ARC. The Advanced Radar Research Center is recognized as the nation's top academic research center on radar. It is taken off of weather radar itself and is expanding well beyond there into a broad array of other opportunities that are out there in the research and development space. We're going to have to build a new building because the research capacity in space wasn't great enough for the facility that we had on campus. And 2021 is a big moment for us. During that time period, there's going to be a recompete for SIMS, for the Cooperative Institute for Mesoscale Meteorological Studies. This could be a contract size of $300 to $525 million that we'll be recompeting for and could expand what we're doing in this place. And so as we sit here tonight, our goal here is to learn and to listen We're going to hear after dinner from Mr. Blum. But I think as we gather here, I just want to say how enjoyable it is to be together. Right? Everyone has choices for their time tonight. But I think being a great university means that we get together as a community, not just in times of crisis, right? Not just in times of obligation, but at moments to actually sit back and think and contemplate our advances and where we can go next. And so it is a special evening. Certainly enjoy your dinner as it is served, and then we'll come back up here and begin the evening. Enjoy your dinner. Thank you. And now it is my absolute pleasure to introduce Mr. Andrew Blum to you. His new book, which hopefully you have a copy of or will soon get a copy of, The Weather Machine, A Journey Inside the Forecast, takes a detailed look at what we all think about, which is the history of weather forecasting and weather prediction. The Weather Machine outlines the tools used over the years, from telegraphs to advanced satellite weather forecasting tools, to help readers understand how the forecast works. And if you look at the books he has done, they're just fascinating. The previous book, Tubes, A Journey to the Center of the Internet, was the first ever book-length work that looked at the physical infrastructure of the Internet. All of the data centers, the undersea cables, and tubes filled with light. It was published in 2012 and to wide acclaim, and has become a national bestseller and has been translated into 10 languages. That's right. It's an impressive reaction. You seem surprised, and yet you haven't heard from him yet. He's a magazine journalist. He has published dozens of feature stories in publications we all know, including Wired, Popular Science, Vanity Fair, the New York Times, the New Yorker, and the Metropolis. As a speaker, he has given over 100 talks at conferences, universities, and corporations. They include Wired, Popular. They include TED Talks, South by Southwest, U.S. State Department, the World Trade Organization, MIT Media Lab, Google, and Microsoft. He holds degrees in literature from Amherst College and human geography from the University of Toronto. He lives in Brooklyn, New York, but is constantly traveling. Please welcome Mr. Andrew Blum.
Hi, good evening. You guys are having a lot more fun than I was expecting you to have. So it's great. It's great to see that. I had a fascinating day today, sort of being toured around and especially visiting the National Weather Center. It's an incredible weather tradition here, both scientific, of course, and also tragic as well. And it's been a real honor to, after working on this book, alone in my office for a few years, to be able to go out into the world and talk about it, particularly to a room with so many passionate weather experts and professional meteorologists as well as experts in those as well. I hope. That said, though, I'm not a meteorologist. I am a journalist. And as such, I go out into the world and I talk to people and I read books and I look in archives and I visit places and I describe what I see. And specifically, I write about big physical things. And I know we don't usually think about the weather forecast as a kind of big physical thing, but I'm going to kind of make an argument for how that's the case. And not only that, but I look at the way that these sort of big physical things that we build, our infrastructures, the way that they express different ideals, and think about why we build what we do, sort of what does it say about who we are, and in particular, how does what we build then make us who we are? We make our institutions, then our institutions make us, and that's absolutely true for the global infrastructure of weather prediction. So what I want to do tonight, I want to look at some of that weather infrastructure and see what it can tell us both about how the weather works, and most importantly, how it keeps improving and how the work that so many of you do can keep it improving even further and faster. I know there's a tradition here and certainly among meteorologists of talking about kind of your storm, the storm that sort of changed your life or got you interested in the subject. For me, my storm was 7 years ago in New York, which was Hurricane Sandy. It was a kind of busy time. My son had just been born. It's the fall of 2012. And there was a Sunday afternoon where I was sitting in a chair, looking at Twitter, sort of as one does, and saw this tweet. I know, look over this direction. We'll sort of point you either here or there. Don't worry, not too many slides. This is Bryan Norcross, kind of one of our most prominent hurricane forecasters. And you can tell at the time Twitter engagement was kind of not quite what it was, and you can tell that there was no such thing as Twitter threads. You had to click off to his blog. But what was remarkable to me was that he had presented a kind of new kind of forecast, something I hadn't really seen before. Specifically, it was a kind of forecast for his forecast. And the way that he put it was that an organized low-pressure system hasn't even formed yet. So a lot can happen, but because the scenario is so dramatic, it's going to require our attention. And that kind of future tense, this idea that it's going to require our attention, made it seem to me like something had changed with the weather forecast, not just in degree, but in kind. 8 days is a long time off. I remember looking out the window, reading this, and seeing that strange sensation where you look out and it's a beautiful day like it is today, and you know that's not going to last for long, and things are going to change pretty dramatically. And I began to realize that he was working way beyond the capabilities that I had come to expect from forecasters. And more specifically than that, he was really placing all of that capability in a very specific place, which was with the weather models. And it went beyond his own sort of expertise and intuition. He was really saying these tools have changed the way that I do what I do. At 6 days out, that first announcement was 8 days out. At 6 days out, he said that very clearly. He said it's not often that credible forecast models consistently forecast a historic event. That was Tuesday. By Thursday, the world was paying attention, and he said the strong evidence we have is that a historic storm is coming, is that every reliable computer forecast model now says it's going to happen. And what struck me was the extent to which, this is among the sort of most prominent and trustworthy hurricane forecasters, and he was very eager to shift the focus not from his own expertise, but from the tools that we had built, from the machines to the infrastructure. Of course, those machines, those models, those tools are themselves built by humans. And I began to get more and more curious about kind of what was going on there, how they were developing, and more strangely, how they were not working always together, how they were kind of unevenly distributed. There's no sound here. You know what he sounds like. And this moment where the European model, my sort of first introduction to this idea, and the American model, the GFS, were saying two very different things about where Hurricane Sandy was going. And I knew computer simulated the weather. That was a sort of, I couldn't think of it how it would be done any other way. That wasn't new to me. But it was strange that this skill could be so unevenly distributed. And when I began to poke around further, it was a black box. I really wanted to know what was going on inside. Even more remarkably, when, of course, the forecast was painfully right. This was what New York looked like after Sandy. It's an amazing photograph by the Dutch photographer Johan Baan. 147 people died in the storm. 650,000 homes were damaged or destroyed. Total losses were around $50 billion. There are gas shortages. More importantly, though, there was a real feeling of fragility, a sense that kind of our infrastructure was not ready for a new era of storms. And I began to formulate something. I began to realize that we had this sort of new type of weather forecasting for a new type of storms. That, as these paradigm shift had kind of happened, fortunately, somewhat ironically, together. And I really wanted to know sort of how had this developed? How had this happened? Where did this weather forecast that had become so much better that I realized so quickly? The meteorologists, of course, today talk about improvements of around a day a decade for the long-term forecast, which is to say a 6-day forecast today is as good as a 5-day forecast 10 years ago. So really, since the iPhone came out, as one example, we can now make our weekend plans on Monday rather than Tuesday. Not all the time, but that's a pretty remarkable and speedy shift. Again, thanks to these improvements in the tools. But to understand how the models work turned out to be a complicated thing, a kind of very closely held knowledge. One of the things that I love about writing about physical infrastructure is that as complex as the code can be, as complex as the math can be, when you write about physical things, there's kind of always something to point at. At some point, there's a kind of hard ground of this, and you can go and you can see this machine, and that doesn't tell you everything, but it does kind of help to ground you with that. And the first thing that I learned about the models was that they weren't meat grinders. You didn't sort of put the weather of the present in and the weather of the forecast came out. On the contrary, it really required thinking about a sort of two Earths was the way that I began to picture it. The sort of comprehensive observation of the atmosphere is the first step, and then this really special ability to speed that forward faster in time to give us what we sort of casually called the forecast, and to recognize that you constantly had these two things working in parallel, and you needed as good an observation as possible. You needed as good science as possible in order to speed them together. You need to be able to line them up. And I started to think about this as kind of three legs of a stool, to think about how we gather these observations, to think about how we understand the atmosphere, this sort of broad topic of science, and then, of course, to think about how we calculate from one to the other, for which we need a sort of good supercomputer. And by coming at this sort of fresh, I could begin to kind of recognize that it wasn't just about more federal funding for a more powerful machine, but it really was about the kind of collaboration required to make all these pieces fit together. And when you look at when you sort of take the starting point of the models and say, okay, this is a kind of point of arrival in a new way, particularly for longer range weather forecasting, medium range weather forecasting, a different history emerges. And I'd read, there are lots of great weather history books, but I was surprised that a lot of the modeling history, because of the success in some ways, is really only the last decade or two, a different history emerges from that. And talk about that a little bit. Does anybody recognize this building? The weather folks, serious science historians? This original Smithsonian institution on the Mall in Washington. The first telegraph was 1844, a line from Washington to Baltimore. Pretty quickly, there was telegraph networks across the United States, and they didn't work in the rain. So when a telegraph operator got to work, they would sort of signal to the people on the other end of the line, and if it wasn't working, they could be pretty sure that rain was coming from that direction. Within a pretty quick, a pretty remarkably speedy development, that was formalized. And I think we kind of were sort of flip about the way in which telecommunications have changed everything. But to really sort of sit back and think and to recognize that the first step towards knowing what the weather is going to be in one place at many times is to realize that we have to know what the weather is in many places at one time. We need that sort of full, that full synoptic view. And because our telecommunications and our sort of this travel across distance is so utterly sort of such a constant in our lives and has been for 100 years, I think we forget that. But at the time, it was a really remarkable leap. Strangely, there's this sort of person to formulate it first was an art critic, an Englishman named John Ruskin, who kind of came up with the idea in 1839, even before there was the first telegraph. It was strange. And he kind of he referred to it right at the beginning as a vast machine. He just calls it a perfect system for methodical and simultaneous observations. Again, I was looking at the maps of the Oklahoma Mesonet today. That's just a given. This is how we do it. But to recognize that sort of leap across space all at the same time is itself an insight is really remarkable. And strangely, when John Ruskin thinks about this in 1839, he puts it here. He writes that where before the solitary dweller in the American prairie observes the passages of the storms, in the future he will find himself a part of one mighty mind, a ray of light entering into one vast eye. And that sort of vast eye image as part of this vast machine, again, it's so familiar to us as a kind of, in an age of surveillance when we are sort of constantly thinking about that. But to have that insight even before the sort of the arrival of the telegraph by a few years is really remarkable to me. The speed at which the networks then develop, it's to the extent that by 1848, the Smithsonian is collecting observations from around the country. When this new building opens in 1855, They put a giant map up in the lobby, and they put up paper discs organized by color when the observations come in. So you have a white disk for fair weather, a black disk for rain, brown for clouds, and blue for snow. And so immediately, there's no forecasting per se, but immediately there's this sort of triumph in the lobby of the Smithsonian of what these kind of observations, transmitted by the new technology, the telegraph, can accomplish. Very quickly, that does become international, but within a couple decades, meteorologists begin to realize that they need a little bit more. Cleveland Abbe, most famously, writes in the 1890s that we've kind of run out of gas with this observation thing. And the way that he puts it is we can never be satisfied until we have a deeper insight into the mechanics of the atmosphere. We must know what they will be and why so. And that question of why this is happening, not just that we're sort of transcending time and space by sort of sending news of the weather beforehand, but really sort of digging deep into it, is a sort of call that goes out and is answered. They were in communication, but the sort of speed at which the work then sort of presented itself is a kind of twist of history. But it's by this guy, Wilhelm Bjerknes, who's a Norwegian meteorologist who meteorologists like to take seriously, but is a little bit off to the side of some of the main weather history. To give some clue of how seriously they take him in Norway, this is the Norwegian Air plane. This is not photoshopped, but they put him on the back of the plane, which I feel like really, is something to consider. I don't know who can make this happen, but we should do it. Sorry, Bjerknes, a very serious guy. He was a physicist. He started working with electricity. But when he began to work out the details, he realized that some of the things that he was thinking about could also be applied to meteorology. And in particular, he sort of came up with this notion that if you could describe the movement of the atmosphere using math and physics, you could be sort of proven right or wrong, the next day, and you could tweak your equations and you could try it again. So he begins to set it up rather as an empirical process, as a real mathematical process, to try to calculate the atmosphere. And he realizes, he sort of boils it down to what are still known as the primitive equations. I imagine a few of you in the room have either sort of suffered through them in class or taught them. He boils them down to sort of based on 7 different variables, but they are all interlinked, and he has no way to calculate them. And more importantly, if you kind of think again about these two Earths, he, as right as the equations end up being, if not particularly useful, he has no perfect observations of the planet. He has no way to calculate them. He has no computer. And so while the sort of basic premise of calculating the evolution of the atmosphere and then determining sort of absolutely if you are right or wrong the next day and then tweaking your equation and doing it again is sound in principle but impossible to execute. It didn't stop in this sort of really bizarre story. This English mathematician Lewis Fry Richardson got wind of this, thought that he could really pull it off if he could only put 64,000 human calculators in a stadium and have each of them do the math when the observations came in and then pass the result to the person standing next to them. And he thought it would make sense to kind of do it as a sort of inverted globe. So you could put the Antarctica in the pit, England in the balcony, and this would work out really well to sort of calculate things. He knew that 64,000 was a little bit unreasonable, but he thought that if you sort of gave them kind of playing fields and cafeterias and things like that, it would sort of make for a nicer work environment. So he sort of simultaneously predicted sort of like parallel computer processing as well as like the Google campus. Just like in one pass. When he did actually sort of do this calculation, actually using Bjerknes's set of observations that Bjerknes had collected, he was sort of famously wrong. The forecast was years late. The resolution was off. The math it didn't quite come together, and that everyone sort of gave up on it essentially for 50 years. Until, in effect, you have the real arrival of atmospheric science as a modern science, until you have the arrival of computers, of satellites, of all the things that we need to actually get those two Earths, to make those two Earths useful for us, to both have a perfect observations or excellent observations of the entire globe, as well as a real understanding of the atmosphere, as well as an ability to put the two of them together. So it is fun to kind of laugh at this notion of a conductor in the middle of these 64,000 equations. What is the stadium seat? 82,000. Okay, so you can handle it. We'll be fine. no problem. But then he called it a forecast factory, and we kind of have it today, less evocatively. This is the European Center for Medium-Range Weather Forecasts, the home of the European model. It does something very similar to the National Weather Service. It does do it, when we talk about global modeling, a little bit better, and I want to talk a little bit about how that is the case. I apologize, it's not a more aesthetically interesting building, but that is the nature of European collaboration. You have your supercomputer. Pictures of supercomputers are also boring. Again, not the point. What is amazing there is what they do with it. Not that it's bigger, but really how they use it. And in particular, at the European Center, half of the compute time is assigned to research, half of it is assigned to operations. And the researchers and the operational scientists are in the building together, and so they're having lunch together. It's a busy cafeteria. They're having a long coffee break in the morning and a long coffee break in the afternoon. And this kind of collaboration, this all being in the same building, ends up having the sort of proof is in the pudding with it, a really meaningful effect on their ability not just to model the atmosphere, but to continually improve that model of the atmosphere. Outside in front in the courtyard is a dry fountain where the scientists who come from all over the world, but primarily from the European countries that are the funders of the European Center, where they bring a rubber ducky from their place, and they put it in front, and this is a tradition that's continued, but is a really, I think, effective way of visualizing the kind of static and collaboration and cooperation that is necessary for essentially good software development. Essentially to make their simulation of the atmosphere closer and closer to the actual observations of the atmosphere, with that special ability to run it forward faster in time. And again, this real recognition of this daily science experiment, this exact thing that Willem Bjerknes described, of predict and verify, tweak, and do it again. And the European Center, of course, is not the only place that does it, but what was remarkable to me was the intimacy of the project to focus on a single global model. And when you look at the numbers, and this will be easier to read for the scientists, but the general gist of it is that this day-a-decade formulation, that the 3-day forecast, the 5-day forecast becomes as good as the 3-day forecast, becomes as good as the 7-day forecast, becomes as good as the 10-day forecast. And at the moment, the curve is not just keeping steady, but is actually accelerating. So the goal there is to predict extreme events 14 days ahead by 2025, which is pretty soon. 2020 is just 6 weeks away. I hope everyone has accomplished what they want to this decade. So I think the other key thing to consider is the way in which, again, this process is handmade. It's really about a lot of scientists working on particular pieces of code and working hard to get their different pieces of the model to work together. And this kind of constant iterative process of improvement. And that half supercomputer for research and half supercomputer for operations means that it's very easy to do these experiments all at once. And that isn't unique in the world, of course, but for an operational center, and when we talk about the importance of the success of these weather forecasts, it's absolutely crucial. I spoke with Jonathan Condor this morning at ABC here, and he said, as many meteorologists do, given the option, and he has the option, this is the model he will use. This is the one he likes. This is the one he trusts the most. And it's quite striking to recognize that it isn't about how big the supercomputer is, but really about what the structure of it is and the way that they're able to marry research and operations in this. And I think certainly a lot of folks in the American weather community are aware of that, and the challenge of putting that together is one to face at the moment. The other challenge is what to do with it. What do we do with a forecast that is almost perfect in strange ways? How do we make decisions based on it? This is from Hurricane Dorian, just in this fall. And what was remarkable to me was the way in which Miami stayed calm while the storm was right offshore. And everybody had confidence that the model said the storm would turn to the north, and it did. And often we talk about the sort of complexity of making decisions when a storm is coming, whether in the near term or the short term, near term or the long term. But in this case, it was really about not making a decision. It was Miami, saying, we have complete faith that this truck coming towards us is going to swerve, and it did. It was, of course, very destructive in many other places. But I thought that was a real sort of amazing kind of banner moment for the way in which these really vastly improved forecasts could be actionable and could help decision makers consider those impacts. And I think I'm really fascinated by the sort of next frontier of the way that when we have better and better weather forecasts, how we deal with them. It's been really interesting to hear here in Oklahoma how, knowing, of course, not a tornado is going to come in 5 days, but knowing that there will be, a real possibility of severe weather in this grid 4 or 5 days out is not just remarkable, but pretty new. It's really, the speed of that is quite improvement. It's quite striking. So if you have one risk, which is a forecast that's too good, the other challenge is how do we keep from screwing it up? I'm not going to sort of rehash the ins and outs of Sharpiegate, as tempting as it is. I think suffice it to say that this was a pretty astounding moment of politics over science. Certainly the global meteorological system, this infrastructure that I'm talking about, is constructed by politics. But Sharpiegate is a really sort of dark moment for the weather community. It was quite sad to see and interesting to talk to people. Not that any federal scientist said anything to me. And it really does as well. It does echo a kind of a broader disregard on the part of this administration for science, for facts, for process. And when you look at the sort of iterative process of improvement of the weather forecast, and you recognize the breadth of institutions and of expertise and of technology and of science that have year by year led to these improvements, and it's quite easy to believe in the institutions that have added to that, and makes it quite difficult to see them, smudged with black marker, I think is the best way to put it. As well, of course, because these infrastructure always kind of expresses our ideas, and because it then makes us, there's the recognition that the sort of the threat to the credibility of our institutions is not only about the trust in the weather forecast, but goes over into so many other realms as well, from the State Department to journalism to that. And I think it's important, there's lots of talk about keeping science out of politics, but to also recognize that science is made by politics, and to recognize that sort of two-way street with that. I think one of the great examples of that was actually with the birth of this global system itself. This is John F. Kennedy addressing the UN in September 1961. It was earlier that year that Yuri Gagarin became the first man in space. It was a few weeks after that that Kennedy makes the famous pledge where he says, we should commit itself to landing a man on the moon and returning him safely to the Earth. What's not often remembered is that was only his first bullet point. In that speech, point number 2 was the development of a nuclear-powered rocket. for exploration. He says perhaps beyond the moon. Point 3 was $50 million for communication satellites. Point 4, now completely forgotten in that speech, was $75 million, and the line was to help us give at the earliest possible time a satellite system for worldwide weather observation. And the worldwide piece of that is absolutely crucial. Kennedy really saw the weather as a point of collaboration between superpowers at just the moment when, of course, there was so much squaring off in other more violent realms. And he brought it up again in this speech, in the September 1961 speech, this time devoted not the sort of famous moonshot speech, but devoted to the threat of nuclear weapons. And he says they must be abolished before they abolish us. And then part of the sort of effort to keep that from happening, to sort of engender global cooperation, becomes, as he puts it, further cooperative efforts between all nations in weather prediction and eventually in weather control. The weather control part we haven't quite gotten to yet. The weather prediction part was taken quite seriously and really almost immediately led to the U.S.-led effort to create this global observation system that has been the backbone of the ability to get that first Earth, the one on the left, the observed Earth, before we then can calculate it forward in time. And it's striking to both recognize the political will behind that, and then, of course, to celebrate the ongoing success of it at just the moment when I think when we unfortunately sort of need it most. The system still depends on that cooperation. This is the group at the World Meteorological Organization Congress that meets every 4 years, most recently in Geneva in June. And when we talk about this global system, it works because of these scientists sort of collaborating together and sort of, bit by bit negotiating the terms of this data exchange. And one of the things that was really the talk of Congress this year was the shift towards different private systems. And a key sort of foundation of the entire global observation system is that everyone shares their data. And as the forecast gets better, as there is more money at stake because of the increase in storms and damage, we're seeing a kind of boom in private weather forecasting. And in a different way than before, we're also seeing the beginnings of private observation systems with private weather satellites, with sort of smartphone-based sensors with different kinds of private data. And so far, the expectation is that all of that is still freely exchanged. But the risk, of course, is that we begin to get more and more of our data from private sources, and we no longer are sharing that data internationally. And you end up with this bifurcation of the system that is essentially 150 years in the making, with some implication that you end up at some point with not just private weather observations, but with private weather models. We were seeing that IBM just announced their private weather model that is offering a sort of forecasting services for parts of the world that have not seen them, a sort of really amazing kind of public good for that. But the direction that it's going in raises the question of, rather than this global public good, a sort of two sets of forecasts, a kind of forecast for the haves and a forecast for the have-nots. Meteorology has been something that governments have always done. And I think, we particularly at this moment, it's crucial to remember that in order to, I think, to continue the success that's been seen. David Grimes, who is the head of the Canadian Weather Service and just finished 8 years as the president of the WMO, the World Meteorological Organization, really sort of makes this point that weather catastrophes attack the most vulnerable. And he really points to governments. He says governments, no matter where they are, feel the obligation to step up. They have a social responsibility to care for their people. That has utterly been the tradition, incredible successful tradition in the U.S. and around the world. I think of Kennedy's point where he said that we live on a planet sort of carved up by borders, yet encased in a borderless atmosphere. And we still do. We always will. So I want to stop there. Thank you.
Good.
I'd be remiss before we wrap up if I didn't do what I've already neglected to do prior to the conclusion, and that is, would all of the members of the larger weather community, School of Meteorology, the National Weather Center, and the broader private community as well, would all of you all stand up and please be recognized for your contributions? It's at events like these that to me truly encapsulate what we do and how it impacts society. I mean, all of those people that just stood up, they're heroes. I mean, the work that they do, and Andrew cataloged it well and chronicled it well over time, but all of us certainly in this room have been impacted by the forecasting models that are out there in a positive way. And when we think about the expense that's associated with this and what it takes to make it work, right? I mean, these partnerships between governments and academia and the private sector, and the fact that there is no getting around being global citizens when it comes to weather, it's stunning and it's important, and there is a fragility to it, and the advances that are occurring are stunning and involve all of us. And so thank you to all of those that are a part of this. Andrew, thank you for the work you've done, which has made an important contribution to the field. And as we look at where we advance as an institution, I love the piece of proselytization here. As we look towards where we choose to invest our time and resources as an institution, this is a place from which we can enhance our impact. And one of my favorite lines to all of our students whenever they ask for advice, and I have very little that's actually useful, but I do love, the approach of what does it all mean? And I think the answer in summary is to love, and if you can, and where you can, make a difference. And being here together and being with those that are involved in the research in this space are truly making a difference. So thank you for being together tonight. We are going to end the way we always end, with Skye Singleton, who has become synonymous with the chant. We've all almost memorized her resume, Norman North graduate, which she made known and proud. She's going to lead us in the chat. As an undergraduate, she was named the Outstanding Senior for the School of Music. She is a recipient of the Marilyn Horne Award and is currently pursuing her doctorate in voice. Please welcome Skye Singleton.
Chant rolls